Hello, my name is Gordon Brebner. I'm currently a senior fellow at AMD, and I work in the AMD Research and Advanced Development, and I'm based in California, in San Jose, California, which is about 60 miles south of San Francisco. And I've been there since 2002. Before then, though, I was a long-term inmate at the University of Edinburgh, so I actually spent 27 years here. Originally as a student and then 21 years on the academic staff, and ultimately I was the professor of computer systems, and I was the last ever head of the computer science department before it became part of the School of Informatics in 1998. So as I said, I work for AMD, but I've only worked for AMD in fact since February last year, 2022. Because originally, and for most of the time in the US, I've worked for a company called Xilinx, which is what I joined in 2002. And they were an FPGA, field programmable gate array company. And it was building on the research I'd been doing at Edinburgh into both field programmable gate arrays and also computer networking. So I joined Xilinx, which, as I say, was acquired, and I was acquired by AMD in 2022. Now, AMD are a very long-running company, which will be a kind of household name to many people, and are well known in the CPU space with x86 architectures, long-term competitor to Intel, and more recently for GPU graphic processor unit architectures. So the kind of merger between the two companies last year brought together a combination of technologies, CPU, GPU from AMD, and also FPGA, programmable logic, and networking technologies from Xilinx. So it's a very exciting place to be in now. It's a much bigger playpen, if you like, for me than it had been for the first 20 years. Now, AMD is a rapidly growing company, I think it would be fair to say, and is quite influential in the overall computer technology market these days. Yeah, this is a tricky one. I've spent about 30 years trying to explain this. Since I first got hooked on the technology in about 1989 here at Edinburgh, I was not a hardware or electronics person, actually. I was a hardcore computer scientist, software kind of person. So what field programmable gate arrays are is the gate array is a kind of two-dimensional array of logic gates, which can do simple logic functions. You can think of them as being and or not kind of functions, but also programmable. So the FP, the field programmable, just means programmable in the field. So you have your hardware chips which can be changed after they've been delivered. You can actually change the logic circuitry and you'll get new hardware. And that's what attracted to me in the first place. I wasn't so interested in just producing fixed hardware, fixed chips which did certain functions, but the whole idea of this being programmable not just before delivery to a customer but afterwards. So that's where the FP for programmable comes from, and the GA is gate array for logic gate array. But it has more historic significance. That term was coined in about 1984, so it's about 40 years old, and it's evolved and advanced a lot since then. So back in 40 years, the reason I got into it was we had one person here at Edinburgh, Tom Keane, who did a PhD supervised by two staff members at that time, John Gray and Art Buchanan, who developed a very simple, it was advanced for the times, field programmable gate array that had a total of 1,024 logic gates. So it was a very small array. It was 32 by 32 cells wide, and they were fairly simple cells. So you couldn't do too much with the technology back in those days. But it was enough for me to get interested. And since 1989, when John Gray was very persuasive in getting me involved, I started looking at that for networking applications. What they did is spin off a startup from Edinburgh. It was one of the first startups, I think, called Algotronics, which a few years later was bought by Xilinx, which was the US-based multinational, acquired Algotronics, and that became the Edinburgh office of Xilinx, which still exists, is now based at the Technopole area of Roslin near the vet school. So, that's advanced, and all these years later still exists as a very successful example of a spin-out from Edinburgh University. And, they've become part of AMD as well as part of the acquisition. So, it started off pretty simple, but just to give perspective, there were 1,000 simple logic gates. These days, contemporary FPGAs have literally millions of far more complex logic gates together with other compute acceleration units. So, things have scaled up enormously, between the 1980s and today, getting on 40 years later. Yeah, P4 has been a focus of mine, well, basically since it emerged, which was in 2014. But let me give you a little bit of the background history. If we go back to the late 1980s when I got involved, I was a software person by background and B, a computer networking person. I was kind of horrified by the hardware design technologies you needed for FPGAs, which were very alien to me. So I've kind of devoted my life since then to making it easier to program these devices, particularly for networking. So when I joined Xilinx in 2002, and this was based on previous research here at Edinburgh, we developed in my research group a succession of, higher level programming experiences for FPGA technology, which were domain specific to packet processing for computer networking. And, in our group, we developed a succession of languages because no real, universal languages existed for this area at the time. So we'd been developing our own languages up until 2014, and we'd collaborated with Stanford a lot on that work, as well as others like Bell Labs. In 2014, P4 was published as a kind of concept paper, and this was intended to become a standard language for network packet processing. And shortly after the paper was published, an organization, a consortium, and it was set up called the P4 Consortium, comprising people from academia and industry to take on, the development and developing a P4 ecosystem. And in those early days, one of the working groups, which was the first working group, was a language design working group, and I co-chaired that from the beginning in 2015. And basically P4 is what's called a domain-specific programming language, which has primitives, or high-level primitives, intended to be good for packet processing and networking. It's not a general-purpose programming language, like C or Java or anything like that. It's specific for implementing networking functions. So we embraced wholeheartedly P4, in my group and in the company, and developed a compiler from the P4 language to FPGA technology, which was one of our successes as a kind of research organization. It became a product in 2014 and still exists, as a product from AMD, which is this compilation flow from the P4 language to FPGA. And the whole idea is finally achieving the dream I had at Edinburgh of having a way of programming FPGAs, using a high-level domain-specific approach, but getting very efficient and high-performance packet processing architectures, which can be used in real-world network switches and network interfaces. Yeah, the general theme of my talk this afternoon is that communication is at least as important as computation. So, when you have a background in computer science like myself, everyone thinks, of the interesting, computational capabilities, processors, memories, algorithms, and software for those. Since a very early age, as it were, at Edinburgh, when I was a student, I got interested in networking, which is where you have communication between computers, and that's been the kind of focus of my life ever since. The original challenge was, just implementing, network interfaces in software. And here at Edinburgh, we had a diverse collection of computers, and how do you connect them together so they can talk to each other? When I was introduced to FPGA technology in 1989, it struck me this could be the ideal programmable hardware technology for implementing networking functions. The thing about networking is whereas compute CPU clock rates have kind of plateaued these days, so one has to do various things like having parallel processing, connecting them together, distributed processing, heterogeneous processing of different kinds of processors. Whereas networking speeds continue to increase, by factors of 2 every few years. And now we're talking about, in our current research, 800 gigabit per second networking rates going on to 1.6 terabit per second. So we have this continuous challenge of how do you get the next 2x factor of speed, and using kind of hardware acceleration and our programming technologies has turned out to be key to that. So really the kind of twofold and integrated achievement, I'd say, over the last 20 years of my kind of industry research group has been a combination of having a high-level programming technique, but then delivering the high-performance networking capabilities that are needed underneath that. So really that's what I would see as the main achievement, the combination of both, not just the high performance, but also the high-level programmability. Currently, there's no signs of a kind of plateau on the networking side. I mean, one thing for sure is the demand on networking communications continues to grow. So nowadays, obviously the big trend is towards AI and machine learning using neural networks, and for training these gigantic neural networks, the kind of thing used in ChatGPT involves huge amounts of computing, but also huge amounts of high-speed networking to connect them together. A single computer cannot train a network of the type used for ChatGPT. And another example is supercomputing, like the Frontier supercomputer, which it's the current top of the top 500, which last year delivered over an exaflop per second of compute, is underpinned by huge amounts of high-speed networking. So this insatiable demand for bigger and bigger models in AI and for high-performance computing is not stopping. And because the CPU side has plateaued, the networking side, I'm biased here, is kind of rescuing that by having continually increased networking rates, which does, of course, pose hardware challenges. We benefit, from shrink factors, in silicon, that the actual silicon being used for chips is decreasing, but also the interfacing for communication. The speeds of these interfaces is continually increasing still. One thing that's heading towards a plateau is the use of copper-based cables, electronic cables for networking. Is heading for a plateau, whereas fiber optics, which is the more widespread and longer distance form of cabling, has a lot of life left in it. So I'm not anticipating an overall plateau, but good thing for we researchers is there's lots of challenges in actually delivering that performance efficiently to the compute things that actually need data. We're essentially the plumbers who are delivering data at high speeds and transferring data from one place to another. So my career path, it's actually been pretty simple to describe, because really I've had 2 jobs in my career. What happened was I came to Edinburgh as an undergraduate in 1975, and unusually in those days I'd done 3 years of kind of computing and computer programming and had fun with that at school before I came. In those days virtually no one had past experience. So I kind of knew I wanted to do computer science, but back then it was still seen as a slightly non-respectable subject, so I actually entered Edinburgh University, signed up to do pure maths, which was meant to be my strength at school. But very rapidly I gravitated and changed to computer science as an undergraduate, and those were kind of wonderful days. It was the kind of early days of computing when a lot of Edinburgh was building its own computers sometimes, building its own operating systems and compilers, and it was a fantastic small department to join. There were only about a dozen or 15 people. So I did my undergraduate degree and stayed on to do a PhD, and then 2 years into that, This probably wouldn't happen these days. I was offered a job on the academic staff, and at the time it involved a significant amount of extra money, and I had to give 9 lectures in the first year. So I signed on enthusiastically. So that became like a 21-year career, in Edinburgh University, Department of Computer Science initially. And in a strange symmetry, I left in 2002 after 21 years on the staff, and now this is my 21st year in industry in the US for Xilinx, and now Xilinx within AMD. So essentially I've had this 2-part career. In my time at Edinburgh, kind of surprising, I discovered early on I actually liked teaching, and devoted quite a lot of attention to that as well as kind of research. And as I said earlier, I got into networking very early as an undergraduate through a fortuitous summer job, and that kind of set the course for my life, having an interest in computer networking. And then I discovered FPGAs in 1989. That was about 8 years into my stint. So, my technical trajectory, for most of the time at Edinburgh was a combination of networking and FPGA. Teaching was always something I liked, but laterally I also got involved in the arcane and Byzantine world of academic management, and ultimately I was head of the computer science department, in fact the last ever head, because in 1998 there was a unification into the School of Informatics where computer science merged with artificial intelligence and cognitive science and the Human Communication Research Centre. So for my last 4 years at Edinburgh, I was part of informatics. All this time I was based at King's Buildings. The George Square Informatics Forum didn't exist till after I left in 2008. So basically, it wasn't a planned move in 2002, but the year before that I'd had a year's sabbatical and spent time in San Jose visiting Xilinx Labs, which was just setting up. The plan was to have a networking group, and basically I got seduced into that. So I kind of transitioned in 2002 to what was promised to be and turned out to be a full-time research job, leading kind of a research group or building a research group and contributing to kind of corporate strategy around networking and communications. And so that's how it began in 2002. I moved to California, and essentially for most of that time it's been a kind of unchanged organization within Xilinx. We had Xilinx Labs, which was a kind of ring-fenced organization reporting directly to the CEO of Xilinx, so we could focus on longer-term projects. And now we're part of AMD, and now we have a merged AMD research organization, which embraces both the former Xilinx Labs and what used to be AMD Research are now combined together, and it's about a 200-person strong organization. So in a way, it was a bit unusual moving to industry as a full-time research thing, because I'd never been a full-time researcher at Edinburgh. I had various other interests on the teaching side and the administration stroke management side. So it's been a slightly different experience. Certainly, in industry, paradoxically, I've published a lot more, and also patents have become a feature there. So I'm getting on 50 patents. Personally, about 100 patents which have come out of my group. So that's a slight difference in industrial research, but that is very much in the spirit of the academic world, and we have a lot of collaborations with some of the top universities around the world, which includes Edinburgh, and Stanford, which is just up the road, has been a particular collaborator of ours over the years. So that's been my career journey. It's been a 2-job career, like 21 years in each today. So there's a nice symmetry in that. And I think I've been very lucky. Things have just happened at the right time in terms of starting my career at Edinburgh and then moving to this different career. And I think it was kind of healthy, for me escaping from Edinburgh. I spent a long time here to actually go somewhere different. But it's great to be back here. My nostalgia memory instantly kicks in when I'm back here in Edinburgh. So it has to be said for me, the work's always been a main preoccupation of mine. I think I've been incredibly lucky in my life that I got to indulge, my favourite hobby for money and personal advancement. So the first thing I'd say, I've been very lucky in terms of being able to pursue my interest in computing and getting paid for it. Away from it. One surprising thing I took up in California, I'd always been allergic to sport, growing up at school, and then in Edinburgh. But shortly after moving to California, a colleague who'd become a marathon runner persuaded me to try out running. So I actually took up running, and very shortly after that ran a few marathons. So I have some marathon medals, which would be very surprising to anyone who ever knew me in Edinburgh, who I avoided exercise and anything like that. Now as I'm getting somewhat older, the running's turned into walking again, walking and hiking, and my wife is very keen on pickleball at the moment, which is the new sport sweeping the USA and I believe in the UK as well, which is a kind of version of ping pong meets tennis meets badminton, and it's kind of designed originally for the older people. There's now professional people, so that's something I might be tempted into on the sporting front, just to get some exercise now the running's gone away. Aside from that, when I was a lot younger, this is before university and school days, I was very interested. This is very nerd-like, buses and trains. And recently I've discovered, in the UK here, there's quite an active community of people of, let's just say, similar age to me and older, who are nostalgic about the buses of the 1960s into the 1970s. And I've actually been tuning into that as a kind of more nostalgia activity, and realizing there were huge amounts of things I didn't know about esoteric aspects of that. So that's something else I've been getting into more recently. But it has to be said though, for me, the work has never really felt like work. I think I've been very lucky to be able to indulge my mainstream interest, in my career, and not many people get that opportunity. So, I'm eternally grateful that the right things came into place. And my time at Edinburgh, was absolutely critical to everything that's happened, basically. So, I'm very contented.